For this problem, we're told to find the voltage, or we have this voltage, V equals 12 cosine 60t plus 45 degrees. It's applied to a 0.1 Henry inductor, and we're told to find the steady state current through this inductor. Okay, the key thing here is to know this table where we have this voltage current relationships between the time and frequency or phasor domain for each element. So we got resistor, inductor, capacitor. So in this case we want to figure out the relationship for the inductor. We're going to look at this equation. Okay, we're going to look at this equation and we're going to use this in applying the steps to find the current. Okay, so let's go ahead and write this down. So for the inductor, we know that V, I'm just going to highlight this, our V is just j omega L times I. Note, just like we did in other examples, our omega here is going to be 60, so we're going to make a note of that. So I'm just going to write it on the side, omega equals 60, and then this is radians per second. Okay, so given the equation, so V in phasor format is going to be j omega L times I. We know we know L, so j omega, we know omega, it's 60, L is going to be 0.1, and then we need to figure out what I is. Alright, so now it's just a matter of rearranging the equation. The other thing we know is we know V. So V, it's given to us here in time domain, but we can convert it easily to the phasor domain. So V in phasor domain is just going to be 12 at an angle of 45 degrees. Okay, so we can substitute that in here, rearrange the equation. I'm going to rearrange this equation. I'm going to say I is equal to V over j 60 times 0.1, okay, like that, and we'll plug in the V, which is 12 at 45 degrees. And here this is going to be J6. Okay, so now it's just a matter of converting between formats, so rectangular and polar formats. Remember, R is going to be the square root of, in this case we got nothing for x, so 0 squared plus 6 squared, which is essentially going to give us 6. Okay, that's going to be our R. If we try to do for angle tangent inverse, we're going to get undefined for 6 over 0. Okay, so this is going to be undefined. However, the better way of doing this is to actually draw it on the real and imaginary axis. Okay, so where we have our real, our imaginary, okay, and then we just have a y component, which is our J6 here, and then this is essentially going to be 90 degrees. Okay, so that's the better way of figuring out what our angle is going to be. In this case, it will be 90 degrees. So let's rewrite this equation. I'm going to write it down here on the side. I is going to equal to 12 at 45 degrees over 6 at 90 degrees. And remember, I'll put this on the side just so you can remember it. When we have Z1 over Z2, it's just simply dividing the amplitudes, and to get the angle you subtract. Okay, so keep that on the side there. So that's what we're going to do. 12 divided by 6 is going to give us 2 at an angle of, in this case we got 45 degrees minus 90, so it's going to give us minus 45 degrees. Okay, so that's our answer in phasor or frequency domain. Now we just got to put it in time domain. So we got to put this in time, and what that gives us is I of t is equal to 2 cosine omega t. We said omega was 60 t minus 45 degrees, and this is going to be in amps, and that's the solution to this problem. Okay, so that's what we get for this problem.